Hello, I will be describing the solution to the problem lava mode. This is problem G. First, let's describe the problem. There is a mountainous area which you're given a map of that area as a rectangle with triangulation. The triangulation is as nice as you can imagine. In particular, no vertex of any triangle lies on the edge of another triangle. The triangles are all non-degenerate, etc. Additionally, you have the constraint that there are no vertices outside of the corners on the east and west edges of the area. For each point of a vertex of a triangulation, you are given its elevation, its height above sea level. And the triangles are planar surfaces, meaning the height at any internal point of a triangle is just the barycentric average or the interpolation from the heights of the three vertices. Given this map, where there might be up to 50,000 triangulation vertices, which implies 100,000 triangles more or less, you are supposed to dig a moat from the east edge to the west edge. The moat should be as short as possible, but the critical constraint here is that all of the moat has to go at one height, meaning all the points that are a part of the moat have to be at the same elevation above sea level. And you're asked what is the shortest possible moat length or to output impossible if no moat is possible. To start solving this problem, first let's see what does the set of points on a given elevation look like. So if you look at a single triangle, since the map, the terrain is linear on that triangle, the elevation, the set of points of the same height on the triangle will just be an interval. Obviously, it might also be degenerate in the sense of it might be just one vertex of a triangle, or it might be just not intersect with a triangle at all. If you look at an adjacent triangle, again, it will be an interval, and since the point on the boundary of the two triangles has the height that we're looking at, it's again going to be an interval. And then if you look at the adjacent triangle, it's again going to be an interval. So what you get is you get this path consisting of intervals within individual triangles. And then, let's say like this. And so you get a path, in this case from the east edge to the west edge. It might also happen that the path, like if you start here, the path might actually happen to hit the north edge, and then it's not a valid mode. Or if you start looking here, the path might actually end up being a cycle. So these three yellow lines that I drew are the sets of points at different elevations. This makes the problem for a specific height look easy. You just kind of start from one edge. If you pick a height, you just go across these vertices here, then here, then here, then here, then here, until you hit some other edge. You cannot cycle because you start from the edge. So until you hit some other edge, if it's the west edge, then you have some candidate mode. Now, what are viable candidate heights? Well, if you shift the height that you're looking at for a bit, the length of every interval within each triangle shifts linearly. So this one gets a bit shorter when you increase the height, this one gets a bit longer, but all these changes are linear as functions of the height. So that means that as long as you don't hit any vertex, the function height to length of moat is linear, and so overall the function is piecewise linear with potential breaks or discontinuities at vertices. This in particular means, a linear function on an interval attains its maximum and minimum on the edges, and so it means that if there exists a solution at all, there exists a solution which passes through a vertex, because otherwise you could shift it a bit and obtain a non-worse solution. And now let's get to the interesting question. What happens when you hit a vertex? So if you start at such a height, you will hit a vertex here, and then there might be multiple triangles for you to try out. Well, there might be, for instance, this triangle, but there might also be this triangle, and there might also be this triangle. So it is possible that you get a bifurcation, that you get multiple different paths to consider when you hit a vertex. This set of observations gives us a quadratic solution. We can just try every single height that is a height of some vertex and just try the unique path, given that there are no points on the eastern border. There's exactly one point, at most one point, of any given height at this border, so we can just follow that path. And then you have one bifurcation which spreads out, but you can notice that all the paths that you consider cross every triangle at most once, and so every single run of such a BFS or DFS or however you choose to code it will encounter every triangle at most once, which means that the runtime of a single search will be linear, and so if you try all the heights, it's going to be quadratic. Now, this is not fast enough. For 100,000 triangles and 50,000 vertices, you cannot try to check every vertex and every vertex height and then go through all the triangles. There are a number of ways to make this run faster in polylog time. I mean, n times log time. So one way to look at this is we sweep through the heights. So if you take the lowest height in the whole map, it's going to be a single vertex, and you will get just a single vertex. Obviously, it's not a path. Now, if you increase the path a bit, you will add edges to some of the triangles that are incident to that vertex. These edges will typically initially form a cycle, but you'll add edges. Now, again, when you increase the path more and more to the next available height, you will, for instance, let's say that this is the first height at which something interesting happens. So then you hit this vertex, and then again the path splits up. So the cycle splits up, and it actually becomes a path. It becomes this path here. And then when you hit this vertex, it splits up again, and you get more paths. At any point in this process, in the process of increasing height, the set of edges that you're looking at is a bunch of paths. If you're looking at a specific vertex height, it might some of these paths might meet at the unique vertex of that height. So the one potential solution is to keep track of these chains, these paths. So you need to have some data structure, which we'll look at in a moment, that is able to maintain a set of intervals. It is able to maintain the length of that set of intervals as a linear function of height. And that has to be summed up, so we have to be able to compute fast the length of the whole chain, which is basically keeping track of a linear function is easy because it's keeping track of the linear coefficient, which is additive, and the constant factor, which is additive. And we need to be able to add and remove vertices from within the middle of that path, these paths. These paths might also be cycle, and we need a cycle, so we also need to handle that. If we are able to perform these operations, so join two paths by adding a new edge, remove an edge from a path, splitting a cycle into a path, or splitting a path into two paths, and calculating the length of a path at a given height, all these in logarithmic time, then we'll be able to solve the problem. There are multiple data structures which you can use for this. I think the most classical one is a treep, which allows you to store which is basically some implementation of a balanced search tree. You can also use skip list. You can also turn this problem into an offline problem. So this is going to be the solution that we, again, sweep across the heights. For each height, maintain the set of chains that are formed by the edges at this particular path. And at any particular height, when we look at the vertex of that height, we just, for all the chains that are incident to that vertex, we check whether this chain is going to the east edge or to the west edge. There's at most one, because there's exactly 1 point of any given height on the east edge and on the west edge. So we have to identify the chain that's going to the east edge, the chain that's going to the west edge, add their lengths, and this is a candidate solution. I'll just mention that this is not the only possible solution. Instead of sweeping by height, you could also consider sweeping by geometry, so sweeping by triangles, maintaining a boundary of triangles. So first this, then it would be this, where you know how expansive is it. Again, you maintain the piecewise linear function from height to distance from the west edge to the current boundary, and the way you expand on the boundary is by adding a new triangle to the boundary. So from here you would go to here. The thing that makes this solution difficult is that you need to take care to make it quadratic, because when you go around the vertex, you might have a path that goes through here and a path that goes through here. And when you're maintaining your piecewise linear function, you need to be able to merge these two paths into one over here again. I will not go into the details of the solution. This is noticeably more complex implementation-wise than the chain solution that I described before. So this is it. I hope you enjoyed both the problem and the solution.